So I'll basically be talking about. Mustansir Burma told you about the probability in physics, and Rajesh talked about probability and statistics in a real life problem. I'll be talking more about random walks and its importance for mathematics. Okay. Yes, and it'll primarily be a history. So, random walks is arguably the simplest stochastic process, and it has been studied for over 100 years. So I'll just talk, and well, it's still being studied, and as Mustansi Burma's talks showed that he started with something which he called a shared history in time, which was the first example was just a random walk going to a Brownian motion. So I'll talk about all those things. And but before that, let me just start where the history of random walks. So Carl Pearson, by the way, is more famous for having had the formal definition, mathematically formal definition of correlation, and to connect it with Partha Majumdar's opening talk, he actually wanted to show that the people in the slum in industrial England were less intelligent than the aristocrats. So he devised this correlation measure, but unfortunately he couldn't, and he was honest enough to say that he couldn't. Okay. So anyway, so the Carl Pearson writes about this problem of the random walk, which let me read. Can any of your readers refer me to a work wherein I should find the solution of the following problem, or failing the knowledge of any existing solution, provide me with an original one? I should be extremely grateful for aid in this matter. And then it says, a man starts from a point O and walks L yards in a straight line. He then turns through any angle, whatever, and walks another L yards in a second straight line. He repeats this process n times. I require the probability that after n of these stretches, he is at a distance between r and r plus delta r from a starting point O. The problem is of considerable interest, but I have only succeeded in obtaining an integrated solution for two stretches, just two individual steps. I think, however, a solution ought to be found, if only in the form of a series of powers of R over n, where n is large. Carl Pearson. So the one thing which actually is very nice about this little question is also tells us how gentle academics was in 100 years ago, rather than the publish or perish regime which we have right now. So here, Lord Rayleigh refers to this paper to which Lord Rayleigh refers to is in modern language. So he actually gives an answer to Carl Pearson's, and his observation is that if a person takes steps of unit length, then after n steps for large n, the probability that the walker lies between x and x plus delta x this is exactly what Mustansir Burma had in one of his first slides, the normal density, which is then it's telling. And as you can see that this density is maximized when x is near 0. So in the next issue of Nature, Carl Pearson thanks Lord Rayleigh and jokingly ended by saying that the lesson of Lord Raleigh's solution is that in open country, the most probable place of finding a drunken man who is at all capable of keeping at his feet is somewhere near his starting point. So this was the starting of the random walk, of the study of random walk, but then it really got developed by George Puglia around 1919 and his 1921 paper in particular. And here he formally sets it up as a random walking problem and on a d-dimensional lattice. Instead of the Carl Pearson at any angle, here it is a d-dimensional lattice. Okay. So the walker moves from a vertex of the lattice, which is a d-dimensional vector of integer coordinates, to its nearest neighboring site in one step. And the randomness comes from the fact that the walker chooses any of the 2D neighboring sites with equal probability. That means it can go either up or down in 2 dimensions or left or right with probability 1/4. In d dimensions, it will be 1 over 2d. So what it does is basically if it has a coordinate x1, x2, xd, then only one of the entries in the coordinates, so let's say xi, changes its value by plus or minus 1. The remaining are the same. Okay. So and the new location is chosen with probability 1 over 2d. In other words, the I is chosen with probability 1 over d, and then whether it's plus 1 or minus 1 is chosen with the additional probability half, together making it 1 over 2d. And the probability at the starting vertex is revisited by the walker in n steps, clearly increases with n, because the probability increases as n increases, that you return to where you started, which is the origin in this particular case. And by the way, Puglia, instead of calling it a random walker, he just called it a wandering point. So the question Puglia asked is, does it approach certainty as n grows without bound? That means that it returns to the starting point. Does it approach certainty as n grows without bound? And in his first paper, he answered basically yes, if it is dimension is 1 or 2, no, if dimension is 3, 4, or 5. And then in a second paper 2 years later, he actually proves it by analytic methods. And the proof is actually, for 1 dimensions, it's so simple that it can actually be stated for school in a high school mathematics book. And so I'll just present it here. And so suppose a walk starts at O, and the walker has to move to the right or to the left. So suppose without loss of generality, the walker moves to the right and comes to R, this location. For the second step, the walker has 2 options. He can either go back to 0, which is given here, returns to O, a probability half event, as we can see in the pictures below, or takes a step to the right, another probability half below. So that's the second step. It can either move back to the site O or move to a new site to the right. So if alpha is the probability that the walker returns to the O, then we see that that there are 3 or 4 possibilities, 3 actually. The walker returns to O at the first step, which is an event with probability half, or in 2, the walker goes further right in the first step, something with probability half, in which case, starting from this third point, which has come from, let's say, the origin 1 and 2, and right now it's at 2, there's a probability alpha that the walker returns to the one immediately left to it, which is the position R. Okay. And once it returns to R, then with probability half, again, it can take a step back, or probability half, it can go to 0. So with the probability half, it takes a step to the right. Then what we have is that alpha is given by this equation. Alpha equals half. Half is because of this green line, or half to the alpha, that's because of the 2a part, or if it goes to the right, then it's alpha squared, because from position 3 it has to come back to position 2 and then again position 1 and then to repeat the entire thing. So the nth term, 1 over 2 to the n plus 1 alpha n, is the probability that the walk made n minus 1 visits to the site R without returning to 0, and on the nth visit, there's a mistake here. On the nth visit to R, it takes a step to the left and goes back to the starting site. So this is the geometric series, and we all know how to add geometric series. And we get that for here, that the unique solution for this is alpha equal to 1. And we can also, in case, so this is called a simple symmetric random walk, because we are taking a step to the left or step to the right with equal probability. In case there's bias, this entire argument can be again rewritten, and in which case we would get alpha is 1 minus absolute value of P minus Q. A natural question to ask is that if a random walk starts from the origin, what is the probability that it reaches minus A, let me call this home, or to B, which let me call it bar. B, of course, stands for bar, right? And we know Carl Pearson talked about the random walk as a drunken man. So if I translate this by length A to the right, then this is the same as starting from A, the random walker reaches home, which is at the origin, or goes to the bar B. Okay. And we want to know what is the probability that it reaches the bar, which is at, sorry, this should be A plus B, there's a mistake, at A plus B before it reaches home. So if PA denotes the probability that starting from A, the walk reaches A plus B before 0, then we see that if the walk takes its first step to the left, an event of probability up, then from there it is PA minus 1 of reaching A plus B. And similarly, if it takes a step to the right, then from there it is probability P of A plus 1. So therefore, we get this equation, which basically says that P of A, the function, the value of P of A minus 1, and P of A plus 1 are all lying on a collinear line, on a straight line. And that tells that for any, all the points P0, P1, up to P of A plus B must lie on a straight line. And then a simple boundary thing, because we know that P of 0 is 0. If you start from 0, you cannot reach the bar because you're stuck there. And if you start from the bar, then of course you start from the bar. You're there already. Because so these are the boundary conditions. And from there we have this solution. Puglia had an alternate description of the random walk in terms of gambling. So now you, as I say jokingly, now you understand why probability is a fun subject. Because a probabilist can legally indulge in various vices like drinking and gambling. Well, as you know, when I was doing my PhD, this is cue to the joke, is that when I was doing my PhD, there was a person who was speaking, and then there's this very famous mathematician, Dinkin, asked him a question at the end of it, and the speaker said, well, I discussed this with my co-author, and my co-author said, if anybody asks you this question, just tell a joke. And we all started laughing. And therefore, there was really no need to tell a joke because we just started laughing at this response. Anyway, so the gambling formulation of this walk is known as the ruin problem, or the Peter and Paul game, which is, so Peter and Paul start with a capital of A and AB respectively. If the coin shows heads, then Peter gives Paul 1 rupee, and if it shows tail, then Paul gives Peter 1 rupee, and this game continues until one of them is bankrupt. The question which we can ask is, on an average, how long does the game last? What is the expected length when either Peter or Paul gets bankrupt? For this, if T of AB is the expected duration of the game, then again we can write a very similar equation, except that we have to have 1 because it takes 1 unit of time to move to either the left or to the right. And if it moves to the right, then Peter's fortune is A plus 1, Paul's fortune is B minus 1, etc. And these are the boundary conditions, just like earlier, except that this has to be 0 because one of them is bankrupt. Yeah, and from here we can actually solve it, and we get the solution as T of AB, the average time, is A times B. Now this. So we generalize this, and this is some little work which I had done. I'll give the references with some co-authors. So instead of just Peter and Paul, let's get Mary also involved. And if for people from the older generation, Peter, Paul, and Mary was a singing, or was a group of singers. So they start with the capitals A, B, and C respectively. What we do is that we first choose a pair of them, either Peter or Paul and Mary, or Mary and Peter, with equal probability. And one way of doing it is to throw a dice. And if the dice shows 1 or 2, then Peter and Paul game. play 3 and 4. If Paul and Mary play, and 5 or 6, then Mary and Peter play. And again, the game stops when one of them is bankrupt. So again, we can write out the equation, and we have the boundary values, which is just given here. The boundary value says that when one of them becomes bankrupt, in other words, see, X is the fortune of Peter, Y is the fortune of Paul, and Z is the fortune of Mary. When one of them becomes 0, then we stop the game. This equation can be solved, and we know that the expected time is 3ABC over A plus B plus C. Again, this is a unique bounded solution. So I want to now phrase it as a random walk problem. So for this, I need to tell you what is a barycentric coordinate. So suppose at any point of time, Peter has 2 rupees, Paul 3, and Mary 2. We write this as a triple, 2, 3, 2. Okay. If Paul and Mary play, that is the second and the third coordinate. And if Mary wins, then the triple becomes, so Mary gets 1 extra rupee, so the triple becomes 2, 2, 3. And similarly, if Paul and Mary play next, from here, then the triple could become 2, 4. Sorry, if Paul had 1, then the triple would become, okay, so this is what's happening. So if this red line says that Paul and Mary played and Mary won. So from 2, 3, 2, if I call this coordinate 2, 3, 2, it has moved to 2, 2, 3. And if Paul had 1, this will move to 2, 4, 1. That's exactly this. Similarly, if Peter and Paul played, then we'll go along this line. And if Paul won, then this would be the case, 1, 4, 2. And if Peter won, then this would become 3, 2, 2. So note a few things. In all those examples, the triple ABC is such that A plus B plus C is a fixed constant. Let's call it S for some. No, please go back. So a valid triple ABC is such that A, B, and C are each non-negative, and the A plus B plus C is a constant S. And the game ends when A, B, or C equals 0. And this is a triangular lattice. This is called a triangular lattice in lattices in graph theory or in mathematics. And that is exactly where, so if you think of one of these vertices as this coordinate 2, 3, 2, and the random walk is moving, has 6 different neighboring edges to move to and go to the vertex, to the neighboring vertex. And this is the equilateral triangle marked in magenta on this triangular lattice. And this equilateral triangle, I'm calling it delta S, because S is the side, the length of the side of this equilateral triangle. So the barycentric coordinate is basically a vertex on the triangular lattice is given a coordinate ABC, where A is the length of the shortest path taken as the number of steps along the triangular lattice from the left edge of S to that point. B is the length of the shortest path from the right edge of S to the point, and C from the bottom edge. So this in particular is 2, 3, 2, because from here, well, this is a mistake. So it should be 3, 2, 2. From here it is 3, from here it is 2, and from here it is 2. So this is a mistake. This should be 3, 2, 2, sorry. So we perform a random walk on this lattice. In other words, what we do is the random walk takes a step with probability 1 over 6 and moves to a new vertex marked by red on the bottom figure with probability 1/6, and the steps it takes is independent of other steps later or earlier. So as I told you, this Peter, Paul, and Mary game led to this random walk. And what can we say if we increase the person? If we have Peter, Paul, Mary, and Jane, we could have done the same kind of analysis. We have a quadruple where A plus B plus C plus D being a constant, and then the entire random walk would be in a tetrahedral lattice. And again, here we can give barycentric coordinates. Okay. However, and we may also write the equation as T of A, B, C, D as 1 plus actually 1 over 12 something. Unfortunately, we do not know how to solve it. So we don't know how to get the expected time of ruin for this game. Okay. Going bankrupt is also called ruin in probability theory. But I want to come back to this. And so around the same time as Carl Pearson was talking about random walks, Einstein studied the movement of small particles suspended in stationary liquids required by the molecular kinetic theory of heat, which Smoluchowski called the kinetic theory of Brownian motion. It was believed for long that the random walk, when speeded up, should start looking like Brownian motion. Monroe-Donsker in 1952 showed that if Sn were to denote the position of the d-dimensional integer lattice at time n of a simple symmetric random walk, simple symmetric means each neighboring edges have equal probability of moving there. Of a simple symmetric random walk starting at the origin, then the diffusively scaled random walk, which is given by this, the Wn of t, which is s of, this is the integer part of n times t divided by square root n, satisfies that the random function Wn converges to the standard Brownian motion on the d-dimensional Euclidean space. I'm, of course, missing out various things. What do I mean by converges? What kind of space I'm talking about? But I'm not going to elaborate on that because this talk is far more for a general audience. So this Wn, as you can see, is a function of t, where t is between 0 and 1. Actually, we can do it for t bigger than 0, and later I will use that also. So as a function, it's a random function. As a function, random function, it's converging to another random function, which is the standard Brownian motion. So now, instead of the space being of integers or lattice points, we've actually moved to the space of all possible functions, or more particularly, all possible continuous functions, because the Brownian motion is a continuous path. So Brownian motion also comes in from a different perspective. So in thermodynamics, this is around 200 years ago, Fourier constructed something called the heat equation, which is the equation given at the bottom of the page, which is the partial with respect to t of u of xt is kappa, the partial squares, del square, del x square of u xt. And this kappa is something called the thermal conductivity of a rod, and it varies from metal to metal. And what he took was basically a rod of length L, and he said, okay, I want to hold the two ends. So at the two ends of the rod, the temperature is 0. Okay, and then the temperature is heated. How does the temperature, as a function of T, and at location X, what is the temperature that is being measured by U of xt? So, and what he says is that, okay, at temperature 0, the rod, the heat distribution on the rod is given by this function g of x, and as I told you, at the two ends of the rod, the temperature is 0. And he used this technique called separation of variables, which he now teach our undergraduate students, and solved this equation. It was a major triumph. And for the mathematically inclined, I'm not going to read this equation. You can read it. You can see there's the germ of a Fourier series here. However, although Fourier came up with the solution, his Fourier series comes much later. So this is around 1805 or so, so around 100 years before Carl Pearson. From a Brownian motion perspective, letting Bt denote the Brownian motion, we know that the probability that starting from a location x, that means B of 0 equal to x, the Brownian motion Bt at time t, the probability that it lies in an interval a to b is given by this quantity where p is exactly similar to what Lord Rayleigh had given as a solution to Carl Pearson's question. So PTX is, for those of you who are familiar, it's basically a normal density with mean x and standard deviation t. Kakutani in 1944 showed that, going back to Fourier's question, that the unique bounded solution to the heat equation, instead of kappa, he had half, but now you can generalize it to kappa. That's quite trivial from half. But this is also called the Dirichlet equation. That the unique bounded solution for this equation with the same boundary conditions as Fourier considered is basically given by the expectation starting from x of g of the location of the Brownian motion at time t. Under the times, this is just a statement saying that we have not yet reached the boundary. The Brownian motion hasn't reached the boundary of the rods, okay, that means 0 or L. And therefore, from the earlier thing, it's given by this integral. So this result actually has nothing to do with being on one dimension 0 to L. It can be given for any d-dimensional in d dimensions for going out of a d-dimensional shape region. And that the Kakutani's theorem works provided the boundary is sufficiently nice. So this delta of d is telling me about the boundary of the domain D. Okay. And here, of course, because, please move back. Here, of course, because it's d dimensions, we have to get the partial derivatives across each of the dimensions. And so taking x to be the vector x1, x2, xd, we can also, the Kakutani tells us how to solve, Kakutani's theorem tells us how to get the solution of u of xt, the temperature at time t at a location x, by this Brownian motion. Since we know from Donskoy's theorem that a random walk, when diffusively scaled, converges to a Brownian motion, from a simulation of the random walk on a fine grid inside a domain D, we may invoke Kakutani's theorem to obtain an approximate solution of the heat equation, and this is done quite frequently. So the random walk can allow us to actually do a simulation and solve a particular PDE. Okay. So another PDE. So this is what I'm saying about the applications of random walk in pure mathematics. Okay. So another PDE of interest is the Poisson equation, which is very similar, except that we had half of the, so this is called the Laplacian, this sum is called the Laplacian. Half of the Laplacian of ux equals -1 for x on a domain. We now, so time doesn't change for just a fixed time, t. And what we're given is that at the boundary, u of z equals 0. Okay. So this is called the Poisson equation. Again, if the boundary of the domain D is nice enough, we know that u of x, again, Kakutani's theorem tells us, a version of Kakutani's theorem tells us that u of x is the expected exit time of a Brownian motion starting from x. So the mean time of exit starting from x is the unique solution, unique bounded solution of the Poisson equation. So we know this. So now let's go back to Peter, Paul, and Mary's game on the triangular lattice. We know that it's equivalent to a random walk on a triangular lattice. The problem here is, again, it was Mustansir problems, that there was correlation. Here the steps in each direction are correlated. Okay, because if Mary moves one step, then Paul must necessarily lose one, Mani or Peter. So the steps in each direction are correlated. Nonetheless, the proof of Donskoy's theorem can be modified to give us that the diffusive scaling, as very similar diffusive scaling of the random walk on the triangular lattice, converges to a two-dimensional Brownian motion. This actually allows us to give an explicit solution of the Poisson equation, half of delta ux equal to -1 for x in an equilateral triangle T, with the boundary condition being uz equal to 0 for z in the boundary of the lattice. And the solution is u of x is 2 by root 3 a times lambda 1, lambda 2, lambda 3. I'll explain what they are. So a is the area of the equilateral triangle, and lambda 1, lambda 2, lambda 3 is the barycentric representation of x. So as you can imagine, the barycentric representation and Cartesian coordinates have a 1-to-1 correspondence. And that's exactly what the thing in red below is telling us, that for x equal to alpha beta, if the Cartesian coordinate is alpha comma beta, then u of x is exactly this formula, where S is the equilateral triangle. Okay. And before I move to the references, let me say that this is the the triangle is the only thing other than a circle or a sphere or something which has a radial symmetry, for which we can solve the Poisson equation explicitly, as we did there. Okay. So let me finish this talk with the references which I have used. So Barry Hughes has, in 1995, has written a book which is really the size of a dictionary, called Random Walks and Random Environments. It was volume 1, which is Random Walks, and volume 2 is supposed to be Random Environments, but that has not yet appeared in print. There's a wonderful set of TIFR lecture notes by Varadhan, called the Lectures on Diffusion Problems and Partial Differential Equations. They're still available on TIFR webpage. And the last part about the Poisson equation comes from a paper of mine with two colleagues from Catalonia. I don't know whether they would like to be called Spanish, which was written around 20 years ago.